Okay, YouTube, in this series of videos, we're going to be discussing the basic premises of all of theoretical probability and how we can use that to find the probability of, say, the union of two events or the probability of events that are occurring in sequence. So let's go ahead and start with some basic vocabulary, starting with an experiment. When we refer to an experiment, we're referring to any happening for which the result is uncertain. So we're basically saying that when we explore probability, we're looking at the theoretical chance that something that is uncertain actually occurs in an experiment. So outcomes. When we talk about the outcomes of an experiment, these are the things that are possibly going to happen. So it doesn't have to happen, but the set of all possible outcomes, that's something we're going to refer to very specially to as our sample space. So when we take all the possible outcomes for an experiment, say like a coin, tails and heads, that set of all possible outcomes is what we refer to as the sample space. And that is kind of contrasted with the event space, which is any sub-collection of a sample space. So what we're going to do here is just very, very quickly, we're going to illustrate what we mean. But this right here would represent the sample space. If we look at this in like a Venn diagram sense. So the sample space is the set of all possible outcomes for an experiment. The event space is just a subset of all the possible outcomes that we're maybe interested in. And we could refer to this here as the event space. And I probably should have written it on the inside. But like if you were to imagine rolling a die, the event that you roll an even, the 2, the 4, and the 6 would be in this little even bubble, and then the 1, 3, and 5 would be out here in the not even bubble to account for all possible outcomes 1 through 6. So the probability of an event, let's go ahead and get to the nitty gritty here. We basically say that if an event E has n of E, now this n of E is basically, we're going to make a little note here, this is the number of outcomes in the sample, or sorry, not the sample space, the event space. So essentially, the number of possible things that give us this particular event and its sample, in our sample space here, basically, let's read through this here. It says if an event E has this many equally likely outcomes and its sample space S has this many equally likely outcomes, then the probability of an event E occurring is P of E. So we're going to read this as the probability of E occurring. We never read the occurring part, but basically the probability of E is equal to the number of ways we could get this in the event space divided by the total number of outcomes here, the number of things in the total sample space. So for instance, if we were to say the probability of rolling a 2 on a die, we would say that really it's just 6 total outcomes. One of them gives us a 2 in that event space, and so the probability is 1 out of 6. So before we get into anything special, what we're going to do is practice finding a sample space. It's going to be imperative to what we need to do. So you notice here it says draw a tree diagram if it helps. Let's do this. To find the sample space or the set of all possible outcomes, we usually write this as a set of things here. And so when we say tossing a coin, what's the set of all possible outcomes that could happen? I would say that it's either going to be a tails or it's going to be a heads, or a heads and a tails. You can listen either way, but this is the sample space for this particular experiment of tossing one coin. Now the moment we toss 2 coins, the interesting thing happens is we could either have like a tails and a tails, or we could have a heads and a heads. And also we have to account for the fact we could get a heads on the first coin, a tails on the second one, or a tails on the first one, and a heads on the second one. But this would be the set of all possible outcomes. You can see that it's 4 times as many as what we started with. Now the interesting thing here is when we toss 3 coins, this is where the tree diagram might come in handy. So what we're going to do is we're going to kind of draw like an original point over here on the left, and we say that for a first experiment, the 2 outcomes, we'll list them here. We say either heads or tails. And so at this point we would say, well, if we were to flip now a second coin, what are its possible outcomes? And its possible outcomes from heads could either be heads or a tails. We get a heads and a heads, or a heads and a tails. Or we get a tails and then a heads, or a tails and then a tails. These are the possible outcomes. So out of these here, we're going to get more branches that pop out of this. And essentially we could see that we get a heads, 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 or a heads, heads, tails. A heads, tails, heads, or a heads, tails, tails. A tails, heads, heads. A tails, heads, tails, or a tails, tails, heads, and a tails, tails, tails. So we can see that tossing 3 coins here, we would have 8 possible outcomes. Excuse me. And we could list them all. We could say heads, 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 tails, tails, tails. Those were listed on the outside here. And we could say heads, heads, tails. We could have a tails, tails, heads. How about a heads, tails, heads, tails, heads, tails, and then a tails, tails, heads, and a heads, tails, tails. Heads, heads, tails. Pardon me. So here are the possible 8 outcomes here, and we should separate these with commas, and I didn't. I'm sorry, but basically the sample space is the set of all possible outcomes for an experiment. So let's go ahead and get into the probability here symbolically. First thing we want to notice here is this. This P of E represents the probability that something actually happens. And the first thing we're saying here is that a probability can be 0, it can be 1, but it's between 0 and 1. And so we'd say is always a number between 0 and 1. Always between 0 and 1, and including 0 and 1. So when we look at things like the probability of an event occurring and we get 0 for an answer, the interesting thing is we'd say that, well, then the probability of the event occurring was there were 0 possible things in the event space over whatever the size of the sample space is. But basically, since nothing gives us that particular event right there, what we get is just a big fat 0. And so if nothing gives us this, we're going to refer to the probability of an event being 0 as an impossible event. And the probability of an event being 1, which is the same as 1.00, which is the same as 100%. Then what we would see here is this. This is what we would refer to as a certain event. That would be something like, if I were to write the probability of an event that's an E there, if I had something like rolling a die and I say roll a number that's 1 or bigger, well, all of them are 1 or bigger. Out of 6 possible, we'd say 1 or 1.00 or a 100% chance. But basically, impossible and certain events have probabilities of 0 and 1, and everything else in between is just some percentage. So let's touch on the idea of a complementary event. We say letting A be an event, and A prime is how we would read this here, A prime, be its complement. Basically, we say if the probability of an event is P of A, the probability of that event A, then the probability of it, excuse me, its complement is the probability of A prime, and that's equal to 1 minus the probability of A. So what I basically want to do here is I want to illustrate this. What we're saying is if this is our entire sample space right here, the sample space, what we have is some event in here. We're going to call this A. Everything that is not on the inside of A is what we call the complement of A. And the definition of A prime, we could say if A is this, then this can be read as not A. And that's what the complement of A means. And so we would say everything on the outside of A within our sample space is A prime. And so the interesting thing here is we have this relationship where if we take the probability of A, which is just this part here, and we add it to the probability of its complement, which is the probability of everything else but it, what we get is we just get the probability of the sample space, or in other words, we just get 1.00 or 100%. So with that being said, what we could say is, well, then if we want to find the probability that something doesn't happen, then what we'll do is we'll take 100% of our stuff here, and we'll subtract off the probability that it does happen, and what you get left with is all this stuff out here where we have the probability of A complement, which is just the whole thing minus the probability that it does happen. So really quickly here, let's talk about unions and intersections. So what you see down here is this kind of Venn diagram representation. In either instance, you're going to see that this S represents the entire set of possible outcomes, the sample space. So we have two events here, A and B, and under this first one here, we're going to write a little note here. We say not mutually exclusive. And underneath this next one here, we're going to write are mutually exclusive. So we say are mutually exclusive. Now, when you exclude something, you leave it out. And mutual means between two things, like a mutual friend or something. So basically, mutually exclusive means that between one another, they have nothing in common. There's a big fat gap between them. These are not mutually exclusive because they share things in common. So with respect to unions and intersections, let's start with a union. We say that A union B, and this is how we write this. We would read it as A union B. Basically means that something can be an A or it can be in B. And so to represent A union B, it'd be either anything in A or B. It could be in either of these things within the sample space. And likewise over here, A or B, it could be in A or it could be in B, but it's in one or the other. That's what we mean by the union. So I always think of this as kind of like the marriage of these two sets together. If you were to marry them together, that would represent the union of those two sets. The empty event. Now, this is interesting. This is a circle with a slash through it. And we refer to this as the null set. And it's the set of things that has nothing in it, basically. So the empty event has no outcome. So when we talk about intersection here right now, as a matter of fact, look at intersection. It is kind of the opposite of this U, which stands for union. I always think of this intersection as kind of like the letter A, because what I'm going to refer to this as is kind of like an and. So when we say A and B or A intersect B, we're saying only the things that these two sets have in common. So when you see A and B right here, we're going to write a little note. This is also referred to as A intersect B, upside down UB, and only refers to the two things that they have in common here. So when we talk about the empty set, and I said I'd bring this up here again in a second, we say if A and B are disjoint, Or we could say if A and B are mutually exclusive, we refer to that as being disjoint. Then we can say that A intersect B has nothing in it. There is nothing that they have in common.